recording in progress.
All right, can you guys quiet, please? So there are two documents I gave you guys. One that's kind of thick, it says Paul's online notes in color. Another one that's black and white, says interval convergence of power series. Let's focus on the smaller one, the black and white one, the one I projected, interval convergence of power series. So the one thing that Ms. York had advised me to do as you guys get ready for BC Calculus next year is to at least have a discussion of a power series. Okay, so we've talked about series, right? Sigma notation, we know what's going on with that. That's no mystery there. And so a power series looks like this. And it's a little bit weird with the notation, but we know what sigma means. It means summation. We know what the bottom means. That's what you start with for n. We know what the top means, where you end. However, there's no end to this, right? Because n is infinity, right? So we're going to do infinite terms. So it's called infinite series as a result, because we're looking at series that are infinite. Now, C sub n is some constant that you're multiplying to this expression that's x minus a raised to the n power. So, for example, if n is 0, it's pretty obvious that x minus a to 0 goes away. And then when you do n is 1, so forth. So you see the pattern, right? You're basically multiplying by this binomial raised some power. Now, a is called the center of your power series, and these are just constants: c0, c1, something, and so forth. These constants are found in when you get to calculus. There's something called the derivative. You'll learn what that is. That's what that will be when you get to calculus. I'm not going to have that discussion because we're not even there yet. We're not even going to get to that until much later. We'll only get to derivatives until much later in spring. But what I do care about is that you understand what convergence means. So convergence means that if I add up all these terms, which is infinite, by the way, terms, ultimately we can find the sum. Sounds kind of weird, right? Like, for example, what if like I had a series like this? It's pretty obvious that I'm multiplying by 3, right? But the thing is that if this is infinite, be able to find the sum of that? No, it's infinite, right? I don't know, right? So there's no convergence here. That doesn't converge, or we say it diverges because we have no clue what that's going to add up to. Just it's infinite, right? But what if I have something like this here? 6 plus 2 plus 2/3 plus 2/9. What's happening here? Yeah. So this is still geometric. So in this case, we multiply by 1/3. There's going to be a convergence here. This is what we call infinite geometric series that converges. And we call this 1/3, excuse me, this 1/3 our common ratio, right? And we're also going to talk about how to find the raised convergence. We're going to have that discussion just a little bit. But we obviously multiply by 1/3. The first term is 6, and we do 1 minus r. So the formula is this: T1 over 1 minus r. This will help me find that sum. Even though this goes on forever, the sum does converge, right? There is a sense of convergence. And if I were to work it out, it'd be 6 over 2/3, which is 9. Yep. So all this adds up to 9. It seems hard to believe, but all that does add up to 9 if you assume infinite terms, right? And so that's what's kind of being discussed over here. Because in essence, you are in some ways somewhat doing a geometric sequence. So you're multiplying by x minus a over and over again. So to find the raised to convergence, there's a little blurb here. The convergence of the series, blah, 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 is described by one of the following 3 cases. There's a positive number r, capital R, which is called the raised to convergence, such that the series diverges for x when x minus a is greater than r, but converges absolutely when it's less than r. The series may or may not converge at either endpoints if x actually equals, if x minus a equals r, basically, or the absolute value of x minus a equals r. The series converges absolutely for every x. If your r happens to be infinity, if your r is 0, sorry, only at x equals and diverges elsewhere. Okay, that stuff doesn't make too much sense just yet. So actually, don't worry about that part just yet. Let's keep moving. Let's look at this example here. I think this will be good for us. And then I have to go back to Paul's online notes, a color copy in just a little bit for you to kind of make sense of all this. So the interval of convergence. Okay, so we're going to talk about that too. Before we do that, let's talk about example 1. Okay, so you see the pattern here, right? You have x to the n power. So when n is 0, you have 1, n is 1, you have x, n is 2, you have x2, and so forth, right? So we look at this and we see for ourselves that this is a geometric sequence, right? You see how this is a geometric sequence? Where do you multiply the top of x per 6? And if you were to go through the algebra, it's a little messy, but if you do this little algebra, like multiply both sides by 1 minus x. And then if you were to, I guess, distribute, so multiply all this by 1, multiply this by negative x. If you were actually go through the motion, do you guys see how this little product works out? You can start with this, which is this.
Everything. Is it just that everything in between?
Yeah, everything between cancels, exactly. So if I get some, yeah, if I get some other,
Oh, I see.
yeah, so you see how like those cancel, those cancel, those cancel, those cancel. So what are you stuck with?
Just that.
You stuck with that. It's 1 minus x raised to n plus 1.
Why did it go to the pencil? So wait, well, are you?
So- Yeah, so what's happening is this. So, but remember, what's what happened on the left side? You didn't have. Yeah, it didn't.
Yeah,
you
but
didn't-
it's,
So Sn will be 1 minus xn over 1 minus x. Yeah,
why does it go from S to the n plus 1?
wait, sorry. Oh, so what's happening? Hold on a sec. 1 sec. Oh, so what they did was we factored out. Good question, actually. Yeah, why did they put it? Fine. So it's 1 minus x to the n times x. Yeah.
So it's a geometric sequence.
Yeah, I think that's. I don't know why. I don't know why that's happening.
Maybe they're saying like x to the n is the same thing.
Yeah, you know what? I think the tree needs to be the same.
Like infinity plus 1.
Yeah, I think that's what's happening. Is that n plus 1 is equal to n. N approaching infinity. I think that's what's happening. Yeah, that's what's happening. Because yes, true. N plus 1 and n are not 100% the same. But if you're assuming n's approaching infinity, which we are, right? Then of course n plus 1 and n are pretty much the same thing. Yeah.
If this is geometric series being summed to limit, why would you not just do P1 over this?
No, I'm showing where we're getting that from. I'm showing where it starts. So what's happening is that now you got this, right? So if you take the limit n approaches infinity, here's the deal. This goes away when x is between -1 and 1. So if x is between -1 and 1, that goes away because if you think about it, let's say x or negative, say x or 1/2. If you raise that to infinity, what's going to happen to that fraction eventually? It becomes 0. It becomes negative form. So you wind up just getting 1 over 1 minus x. And remember, 1 was our first term. And we have 1 minus x there. So this kind of so this would converge when this happens, and we call this the interval of convergence. Because this interval allows us to have the sum converge. We also say that the radius of convergence. Let me erase the board. We also say that the radius of convergence is from is -1. Sorry, it's +1. Because it's the same thing as saying from -1 to 1. So if you think of a number line, right? Let's get a highlighter here. What's the center here? 0. And how far is 0 from either endpoint? So in this particular case, a geometric power series, we'd say that the radius is 1, and the interval of convergence is from -1 to 1. Let me show you a problem that we're actually going to be working on the homework in just a little bit. So let's look at this next one here. And this is the part that's going to be a little tricky, and this is why we need to pause on online notes to help us out here. Okay, so you have something called another power series, right? And let me erase the board.
Okay, so here's another power series, right? So the first term is 1, the next term is -1/2 times x minus 2, the next one is positive 1/4 x minus 2 squared minus plus. What pattern are you noticing in the sequence here? The signs alternate, right? X minus 2 is gets rid of 1 power, 2nd power, 3rd power, 4th power. Also, it's 1/2, 1/4. Looks like that's rid of the n power. So in general,
A sequence follows this. This is my general term. This is the stuff that the AP Calc BC students are working on over the last couple of months or so. They're working on this kind of stuff. So we say the center is at 2. Okay. And we know what C0, C1, blah, blah, blah. So then what you do, hold on, where are you? Then what you do, we know that we only get convergence when this happens. We only get convergence when that happens. When the common ratio, so R is what we call the common ratio, little r, is a common ratio. And what you're trying to do is you're trying to force the series to be an infinite geoseries that converges. So you're actually forcing the issue. You want this series to converge and act like a geometric series. That's what you want. So how do you do this? What you do is you do something called the ratio test. It's a little confusing. I'm going to kind of walk you guys through it, and then we're going to look at Paul's online notes because it has a better way of explaining it to you. Here's how the ratio test works. You take, basically you're doing this. You're doing T m plus 1 over Tn. That's called the ratio test. And what do we expect this to happen? We expect this to be less than 1, right? Because guess what?
Tn plus over Tn. If this is a geometric sequence, right? What should this all equal? So R, exactly. You want R to be less than 1, right? But this could be valid.
For this to actually force the issue. So you're forcing it to be less than 1. So what did they do over here? This is the part that's most critical. What happened was you took this general term, you added, you replaced n with n plus 1. So they had -1/2 n plus 1 times x minus 2 raised to the n plus 1 all over -1/2 raised to the n times x minus 2 raised to the n power. That's essentially what they did there. Well, guess what?
We divide these two together. -1/2 n plus 1, -1/2 to the n. How's that reduce? We have just -1/2 because n's cancel, right? That's just -1/2. What happens here if x minus 2 to the n plus 1 or x minus 2 to the n? What does that produce? X minus 2. So you're stuck now.
With just -1/2 times x minus 2. And that right there has to be less than 1. But because we have to make sure it doesn't go too far less than 1, because you don't want R to be -2, that'd be a problem. So you have to capture it between -1 and 1, or the absolute value of that expression has to be less than 1. So if you were to work that out, you realize, okay, well, I have the absolute value of negative x minus 2 over 2. The negative just goes away because it's absolute value. So that's if x minus 2 over 2 has to be less than 1. Well, bottom line is that you need this to be less than 2. And you've done this in the past. You've solved absolute value inequalities in the past. X minus 2 is less than 2, or x minus 2 has to be greater than -2. So x has got to be less than 4, or x has to be greater than 0. Hence, your interval of convergence is from 0 to 4. So as long as x is between 0 and 4, this will converge. As long as x is between 0 and 4. And also, if we think about going from 0 to 4, what's the average? What's the middle between 0 and 4? 2, right? Of course, 2 we can use n1. So your radius is going to be 2 as well. So we all say the radius is 2.
Well, is that just an relation? I think that's a.
Exactly, right. So let's try this again. But let me actually hide the solution. Well, actually, you guys can see the solutions. I'm going to hide it. So maybe don't look at it. And let's try it again so we can actually find the interval of convergence. So let's try it again. I'll do it up here. So you may want to hide it. So this is a really wacky series, right? -1 raised to n minus 1, which means there's an alternation between negative and positive signs. X to the n over n, fine, whatever that is, right? So you're going to do Tn plus 1 over Tn. And the absolute value of that has to be less than 1. This is called the ratio test. There are actually a bunch of other tests you do for convergence. There's something called a root test, an integral test, a divergence test, harmonic series test. I'm not going to go down that path because that's all Precalculus. See, I want to give you just a taste, give you a little teaser, like this is something I think you guys can handle because the math is not so bad. But just give you guys some exposure, just so when you do see this a year from now, like, okay, at least we're doing this, so it's not brand new to me. So that's kind of the thinking here. So let's replace n with n plus 1. So if I do that, I'm going to have -1. I'm going to replace n with n plus 1. So you have n plus 1 minus 1 times x raised to n plus 1 over n plus 1. Whole thing, -1 raised to the n minus 1 times x to the n over n. Does that make sense what I just did? We're good so far? Yeah? No questions? Okay. Now you got to reduce. When you reduce, here's what I suggest you do. Kind of break it up piecemeal. So, for example, those just cancel, right? So you have -1 raised to the n over -1 raised to the n minus 1 times x to the n plus 1 over n plus 1. And you flip the other guy, right? Make sense so far? Yes, no? Okay.
Use your properties of exponents. Do these have the same base? Yes. How do we combine these exponents? They have the same base and divide. So it becomes just -1 to the 1 power.
And we have x to the n plus 1 over x to the n. How's that? What does that become? Just x times n over n plus 1. Or, in essence, you get -x times n over n plus 1. And that absolute value has to be less than 1. So again, we're trying to force the issue here. Now, what is n approaching as, I mean, what in general, like, what are we trying to, these are infinite series, right? So n's approaching infinity. What happens when we have a rational expression like this when the degrees are the same? What does that reduce to when n's approaching infinity? 1. Good. So the absolute of x has to be, which is just basically x, right? I mean, sorry, absolute -x is absolute of x has to be less than 1. So your interval of convergence will be from -1 to 1. So as long as x is between -1 and 1, this will converge. And that's how you prove it. That's a proof you have to do. Sure. So let's back a little bit. So what I did was, when you do the ratio test, when you're going to be looking at the one term each way out, you take the ratio. You want that ratio to be less than 1, because that will make it, you know, see something. You notice. So what I did is I took this next here, right? I replaced the answer n plus 1. So that's what I got. Come on, down here, right? N plus 1 minus 1, right? And then of course x n plus 1 over n plus 1. And then divided by Tn, which is this right here. Then what I did was I said, okay, let me break this apart. So -1 to the n over -1 to n plus 1 minus 1. Subtract those exponents, that's -1 to 1. Then here, I have two fractions of divided, so I flip the bottom fraction. So I get that. Now I see an opportunity to cancel this out. That comes x to 1 power. And that's just n over n plus 1.
Yeah, I just put the last thing out.
Yeah, so now the absolute of this has plus 1. Well, remember, what's n approaching? infinity, right? We know what happens when you have a rational expression, right? When you have, let's say, x to the third power plus dot dot dot, 2x to the third power plus dot dot dot, and you're letting x approach infinity. Well, ultimately, what's going to happen is that when these degrees are the same, you take the ratio of leading coefficients. These degrees are the same. You take the ratio of leading coefficients. So essentially, do something called the limits. You take the limits and approach infinity, which is 1. Now, if that were 2 milligram plus 1, then I'd be on -2x. Yeah.
So just to clarify, the radius convergence points, I would say.
The interval of convergence is basically what values of x you're allowed to use to guarantee some that converges.
The radius.
And then the radius is simply just from the center to either endpoint.
Oh, the radius. Okay.
From the center to either endpoint, right?
So the radius.
Right. Yeah. Let me put this in the text box so you guys are more clear on it. So the interval of convergence, that might help. The interval of convergence represents all x values that enable the sum of the series to converge. Okay, that's interval of convergence. Actually, let me switch that to red. There we go. Okay, then the radius is computed by taking the middle of the interval and subtracting it from either endpoint of the interval. Actually, yeah, it is. That is what it is. Yeah. Let me just, that's better. Yeah. Yeah. Is the average of the endpoints. Wait, no.
The center to end.
Yeah. I think how I had it earlier was correct. Matthew, go ahead. Yeah, the radius is simply the difference between either endpoint and the center of the interval. Yeah, that's a better way of saying it. There we go. And it's a positive value. So the homework that I'm gonna have you guys do over the weekend, there's a few more examples as well. But the homework I have you do is going to be basically find the interval of convergence of each of these series, but using the ratio tests. You're going to be using the ratio test every single time. So let's look at like a couple more just so you guys get the idea of what's going on here. With the exclamation point. Don't worry about that for now. I'm not going to go down that path. That's a great question. I'm not. Yes, but exactly what Brooke said. I'm not going to go that rabbit hole. Yes, great question, Catherine. I'm not going to go down that path today. Yeah, Matthew. Yeah. Are you guys leave right now? You and Andy both. Yeah. If you guys need to go now. Yeah. They said 10:50, but that's what said online. But if you need to go 10:40, you know better than I do. I don't know. Hold on. She did. Wait, what's the teacher's name again? You know what? It's fine. You guys go. It's fine. I trust you guys. You go ahead. You're fine. Yeah. Okay, guys, quiet, please. Thank you. All right. So, guys, I'm not done talking. Let me finish. Thank you. All right. So let's look at the next one here. And again, don't worry about the whole harmonic flickers. Like, I don't want to go down that path. All right. Next one. You guys know what factorial is? Have you guys seen that? Yeah. Yeah. It's basically n, n minus 1, n minus 2, n minus 3, n minus 4. So whatever like 4 factorial
n plus one. That flipped over. So when you combine things, you realize the fact that with x n plus one x n is x. And then n plus one factorial n plus one times n factorial. The n factorials cancel, get that. And you need this, you need aspect of x to basically converge to you need to less than one. However, it's not going to matter. Right? It's not going to matter because if n's approaching infinity, overall, what does this become? 0, right? Yeah. And so as long as this whole ratio is less than 1, we're going to converge. That's part of the ratio. As long as whatever we're calculating, whether this is less than 1, but it's going to be less than 1, this can be 0 anyway. So in this case, x can be whatever. It doesn't matter. X can be whatever. This will always converge.
Because overall, when n's approaching infinity, so that's the last thing you have to do is let n approach infinity. You'd see that, well, it doesn't matter. The whole thing becomes 0 anyway. And as long as that ratio is less than 1, you're going to be good. So this converges everywhere. Here's another one that looks also kind of nasty, right? But again, replace that with n plus 1. Do the algebra, work it out. If you do the algebra correctly, you should get this expression here. Now, here's the deal. Let n approach infinity, you're going to get x over 3. That has to be less than 1, or actually x has to be less than 3. So the interval will converge from -3 to 3. And hence your radius will be 3. And so you have that as well. So you have these worked out examples to look at. Now, going back to Paul's online notes, which, by the way, this is a great resource. We want to talk to PC, great resource. So they first kind of explain, hey, what is a factorial and blah, blah, blah. They kind of give you some stuff there. If you have 2n factorial, they give some examples there. And then they show you, oh, here's the ratio test, right? Just exactly as I explained, you take the limit of this expression as n approaches infinity. If the limit is less than 1, you're going to converge. Great one, you're going to diverge. Equals 1, there's some funny business. We're not going to get into that funny business. I don't want to get into that rabbit hole. But they give some examples, they work it out, and you get the answer, right? So you give you all these different proofs here. There's actually a formal proof of it right at the bottom, in case you're curious how it looks. But really, the big thing is focus on the smaller packet and do these 12 problems. So that's what you're doing. The answer is down below. If you get stuck, let me know. But what you're going to do for each case, you're going to do the ratio test, do the algebra, make sure the absolute value of your ratio is less than 1, solve for x, and that'll be your interval convergence.
Like, my
Don't worry about that. We're not going to do that today. Yeah, I do see that in some cases that is happening with like 1 and 9 and 7. But I'm not going to worry about that. So for now, I just want you guys to get the notions of just doing the ratio test and find the interval of convergence. So I'm all done.